Lens principle. And in particular, for this, then what happens is that there can be kind of wave functions for particles to be analyzed. And for these wave functions, for the spectral analysis, there are two types of contributions can be analyzed, and one is of non-gravitation of forces of quantum origin and components due to quantum interactions, and the other components are those which are due to gravitational to the gravitational contributions. And to do so, it's necessary to find a measure for which the complete system can be integrated. That means that how to what kind of measures to use in the spectral analysis for the Fourier decomposition. And to do so, in particular, that means for better analyzing the contributions of possible quantum gravitational features of the gravitational force, it's necessary to look at high energies if we are looking for Earth-based experiments or laser field experiments, for the reasons I will try to illustrate. And in particular, there can be the different kind of contributions can be analyzed. I made some examples, and the further references are given within the slides. And so can you see my arrow? No, you cannot see my pointer. We see the spectral analysis for the energy levels of a particle, for which one kind of energy levels in their spectral analysis are due to gravitational force, and the other one to non-gravitational forces. And for this, for the present data, for the comparison of the present data, it's necessary to look for order of c to the -2 power -6, where c is the velocity of light for the gravitational effects, and to h bar to power to the -2 to for the the quantum contributions. And for this, we also need a measure which can be for which, according to the space on which the wave functions are defined, we need to look at subgroups of the algebra SL to R. And so for the differential measures, we need the precise subgroup is not defined yet, and in particular it depends whether we are looking for Minkowskian flat spacetime or a relativistic spacetime. And among the possible implementations of the quantization, for this, it's necessary to specify what kind of gravitational background is considered, and in particular if Einsteinian gravity is considered, or if other kind of gravitational systems are considered. And in particular, the algebraic structures for the Minkowski spacetime are known, and for a different kind of spacetimes, I will have some analysis. And in particular, the measure has to contain the subgroups of S2R have to contain the physical transformations which are present in both in the Einsteinian setting or from other contributions, which contribute to the gravitational force without being Einsteinian, which are not excluded theoretically, but which are not have not been experimentally detected yet. And in particular, it's necessary to look for a description which can allow to describe stationarity of free states if they are not perturbed, or the time dependence of the perturbation. And in particular, one kind of analysis can be one due to the gravitomagnetic effect, for which it's possible to find, as you see in the first point of the equation, a split of the energy level, and which can receive contributions also from faraway gravitational bodies, as I will show. And the correction which is due to this effect can be calculated as order of c to the power -5. And the perturbation due to the some kind of celestial bodies can be described by Legendre polynomials, which have non-vanishing contributions, and in particular they obey some specific law, which I can explain better if I am asked about. And but in particular, there is also the Newman-Penrose formalism, which allows to describe the component of the gravitational effects due to the celestial bodies, which which can arrive on Earth-based experiments, and they are named psi F2, which is, if you cannot see my pointer, which is indicated after equation number 10. And they, so they are calculated in the formalism, which is called the post-Newtonian, and the energy flux available depends on the velocity of the particle considered, which is perturbing the celestial body at a suitable post-Newtonian order. Post-Newtonian means which we are means that we are considering general relativistic effects. And in particular, one kind of system which can give such a non-vanishing contribution is a spherical perturbation of a spherical symmetric metric. And it can be calculated both in the case of a Schwarzschild metric or in the case of Kerr black holes, for example. They have been calculated. And so it's necessary to extend, for this case, a double cross-check of the spectral analysis, and to consider the maximal contributions which can be obtained from the gravitational force, which have been commented. And so in particular, it's necessary to define the test mass equalities for the coordinate time and proper time in the case of Kerr metric, which depend also on some geometrical objects such as the rigid tensor, whose contribution arrive to order of C power -4. And it's possible to consider also other models of gravity, which are teleparallel models of gravities, which contain the torsion field, and also the interaction of spinning test particle in the Kerr metric, preferred direction of the observable universe, which can be compared to the CMB direction, and the kind of interaction which they can have with test particles, for example, electrons, and also from cosmic anisotropy. That means the coupling with to define the Hamiltonian in the last formula, which describes the considered coupling, possible couplings which do not violate the available data and which have been evaluated numerically. So it's possible to consider also kind of fifth force interaction, which can be studied in for neutrinos, and they should be they can be parameterized by studying systems in interferometers and without postulating neutrino-neutrino interaction, but only fifth force contributions. And the potential due to the fifth force can be expressed as in the first equation, but can be also majorized in the second equation, which we call V5, for which we call V5 the potential, for which can be majorized by considering running constants. And so this way it's possible to analyze the ratio between the evaluated gravitational constants and the constant due to the postulated fifth force. And this can be done in interferometers by evaluating the discrepancies between geodesics, which massless neutrino should follow, and the experimentally calculated possible deviations from the geodesics. And for this, it's also possible to reverse, as in the last equation, it's possible to reverse the analysis in order to obtain, to evaluate the coupling constant of the fifth force. And for this, it is necessary to look for displacements in at least two directions. So far we can arrive to see what is the equivalent of the possible perturbations of particles for their optical system equivalents, which are which can be quantum optical systems or optical systems, for which the quantum nature of the phenomena analyzed is extended on a space range which is much bigger than the Planck length. And for this, we need a density operator should be defined. And if we look at laser fields, for example, at very high energies, the calculation of the density operator needs kinds of approximations, and these calculations can be done both in the case when the Fock space the description is not applicable because of very high energy states or infinite energy states. And this way also the number operator should not be employed. So the analysis can be done by defining a weighting function on a compact support, for which it's possible to better evaluate the energy of the states, the description of the wave functions for the very high energy states or infinite energy states. And in particular, it's possible to look at one other problem is the definition of quantum optical systems for Gaussian. In the case of semi-classical systems, they can be defined both for Gaussian wave packets and for non-Gaussian wave packets. And so it's possible to define an approximation with the previous definitions. It's possible to evaluate an approximation for the weighting support function and approximation for according to the presence of different parameters, and also to define the needed expression for the operators for which the density matrix should be computed. And it's possible also to look at applications of the results, in particular the long time limit for the error estimation, which can be formulated both numerically or theoretically, and it's expressed in equation 1, and in equation 2 there is the result evaluated by the method previously exposed. And it's also possible to look for the Fourier decomposition with the proper measure, for which it's possible to compare the semi-classical states with those for the optical system, and also to look what happens to systems which extend over the Planck length. And for particles with very high momentum, for which also infinite energy states can be put within the approximation of equation 2. And as another application, there can be experimental apparatus techniques with cold atomic ensembles. The results can be applied also to cold atomic trapped ions and jump processes between states. and quantum correlation of multispatial modes for Gauss Markov models, uncertainty estimations in quantum metrology, and the coherence of dissipation for mixed controlled collections of highly intensively energetic laser fields after the application of a good definition of the level of the energy states and of the measure. And other kind of contributions to the spectral analysis are those due to the presence of fractionally charged particles within the terrestrial crust, for which